So this particular section is to do with when t equal to infinity. So this is infinite horizon problems. And in many cases, infinite horizon problems sometimes are simpler. It's because the time t, if the problem is stationary, then you don't need to worry about time t. So the solution, which is the feedback control, only depends on x, which is the state. And so because it is single dimension, then, I mean, single means only the state space. You don't need the extra dimension of time. Now, the other reason is that people don't know sometimes what is a finite horizon. You know, companies, if you ask a company what is their finite horizon, what does that mean? You know, is the company going to fold after that finite horizon, or the company is an ongoing concern? So, you know, what it means basically is that you solve the t equal to infinity problem when A, you don't know, you know, if the company or the society is an ongoing concern, then t equal to infinity is a good approximation. It is an approximation of a large time t, whatever that happens to be, which we don't know. Okay. So it approximates large time horizon problems, and it simplifies the analysis. So there's a lot of work, you know, if you look at the economics problems, most of them are infinite horizon problems anyway, because they don't like the complication of small t in their solution. Okay. So when t equal to infinity, we need a discount rate. If you don't have a discount rate, then the value function or the objective function, the maximum, the objective function will blow up on you. It'll become infinity. And so then there are many, many controls that will give you infinite solution. And so you really don't know what is optimal. And then you need to worry about another kind of theory to select from various different solutions, which all give infinity, to find out which is good one. So you need another kind of criteria. And there are other criteria that are available, but I'm not going to get into that right now. So if there's a non-stationary infinite horizon problem, then these problems are very hard to solve. And also one doesn't know, you know, how do you forecast all the way to infinity anyway? Because non-stationary means there are time functions. And that means that's a forecast. It's a deterministic problem that is a forecast. And you have no good idea of, you know, what the forecast should be. We'll talk about this a little bit in chapter 6 about what happens to a forecast and issues of forecast issues that come into play. So basically, we need infinite horizon problem. We are in this particular chapter or section, and we need stationary problem so that all the functions that are involved, other than e to the minus rho t, which is the discount factor, are independent of time t. Okay. The current value Hamiltonian is independent of time t. Current value Hamiltonian does not require e to the minus rho t. That is a standard Hamiltonian. The current value Hamiltonian, don't put e to the minus rho t. So that's basically what that means. That sigma is a typo. This should be psi. It's a salvage value function. That sigma was at one time sigma, but now sigma has become very volatility in chapter 13. And so we have to remove this sigma somehow. It did not get changed. So this should be psi, small psi, which is the salvage value in the current value formulation. Okay. I don't think we had something about autonomous system in an exercise. Let's not worry about that too much. I don't think in this class we have much to do with autonomous system, but if you run into literature, you can always come back to it. So here then psi is 0. So if you put psi equal to 0, we have a problem like this. The reason we put psi equal to 0 is because what is the salvage value at infinity? And now that is not a simple issue. There are some delicate aspects of that problem, which we will talk a little bit more about in chapter 5 when we talk about finance problems. But for the time being, in most infinite horizon problems, usually because there is no end to the horizon, there is no need for salvage value. Okay? If there's a salvage value, it has to be a limiting value. And that then has some issues that we can talk about later in chapter 5. But that's the standard formulation of an infinite horizon stationary problem with a discount rate of rho. Most of the economics people will have this kind of section, but they will not do this. They don't like constraints. So they use first order conditions in most cases when they maximize Hamiltonian. And so this is new. This is new. I don't see any economics book that does that. This is my book is the only one that does it. And it's a generalization of what is available in the literature. So sort of going back to, if you have the book, you can go back to 2.73. This is where we proved the sufficiency condition of the optimal control. And because S is 0, if you put S equal to 0 and T equal to infinity, then that equation reduces to this equation. In 2.73, we had a present value, so we call this the present value. But lambda present value T is nothing but e to the minus rho T current value lambda T. So then you can, so that's straight limit with S equal to 0 in 2.73. And then T going to infinity, then lambda PV becomes e to the minus rho T lambda T. So that equation just comes from 2.73. When the free endpoint, which means free endpoint means there is no terminal constraint. If there is no terminal constraint on time, then xt is arbitrary. And when x is arbitrary, you can go to 3.97 and you basically have a problem because with this arbitrary, you cannot control much about it. So what remains is you remove this, and what remains is these conditions. You can sort of see that when it's a free endpoint case in a finite horizon problem, free endpoint case in a finite horizon problem says lambda t equal to 0, right? But in an infinite horizon problem, it is not necessary that lambda t is 0. All you need is that the lambda t doesn't grow as fast as rho. So the product of this goes to 0. Okay, so that's kind of a subtle point that you might want to think about. If we have a non-negative constraint, which is this kind of constraint, so once again, you have a complementary slackness kind of conditions. So if you go back to 3.98, this is a clear transversality condition, and this limit implied 3.98. 3.98 is right there. Okay. So now there's an example. We now have an example going from 0 to infinity. We have a utility of consumption, which is log of C of t. And we are discounting the utility by discount factor e to the minus rho t, or discount rate rho. This is called discount factor. Rho is called discount rate. And we don't want to go bankrupt. So we want solvent forever. Okay, which means that we want Wt to be bigger than or equal to 0 as t goes to infinity. Okay. It turns out that that's the interest rate that you get on your wealth. This is the consumption, so your W dot, which is the rate of change of wealth, is going like this. We have initial wealth W0, which is assumed to be bigger than 0. So we want to consume in such a way so we maximize this function. We want CT to be bigger than or equal to 0, and we want the wealth to be always positive. So going from our limiting version, these are going to be the conditions, which are the transversality conditions. And if you go back to the example, but we solved that example, by the way, for finite horizon, then we can go back to that example and put t equal to infinity, and we get this. So we get W star t to be this, which is the wealth at time t. And you can see that it's growing at rate R, but it's declining at rho because we are consuming in some way, and so the wealth is increasing because of the interest rate, and then also consuming, which depends on the discount rate as well. And then we have a consumption, which is rho times WT. So higher the rho, higher the consumption, because higher rho means you don't want to postpone the consumption. And so you want to have a more consumption, and so that would decrease the wealth faster. And that means the consumption in the future will decrease, will be lower. Of course, it depends on R as well. But if R was fixed and all we do is change rho, then this will become lower than for a less rho where you consume less. Okay, so that's basically what that means. This is also, you can use that limit as well. St goes to infinity in 3.51, or you can actually put that consumption function right in there, here, and you can compute this integral. Either way, you have an objective function. Now, when t equal to infinity, one would like to know what happens in equilibrium. So equilibrium is, as t goes to infinity, this path reaches some asymptotic value, So we want to find out what is that. Okay, so we want to find out what that. For that, we don't have to go through this exercise. We can actually go through a formula of this kind, so we can see what's going on. Clearly, in the case of stationary system, equilibrium means that nothing changes. So x dot becomes 0, lambda dot becomes 0. So once you have x dot equal to lambda dot equal to 0, x dot equal to 0 gives you this. This is our equilibrium solution, x bar, u bar, lambda bar, mu bar. So then at that solution, x dot is 0, lambda dot is 0. And of course, we need the condition, this constraint to be satisfied, so a complementary slackness condition. And we have a Hamiltonian maximization subject to u that satisfies this constraint. Notice that if I don't have that constraint G, then this goes away and this goes away. And then you basically have 1, 2, and 3. This is called a triple. So if you look at, this is a quadruple, but if you don't mu, then this is a triple, and triple is defined by these three equations. The three equations are given by x dot equal to 0, lambda dot equal to 0, and Hamiltonian being maximized. And Hamiltonian being maximized, you can actually set control. You maximizing the Hamiltonian with respect to u, so a first order condition gives you this h sub u equal to 0. If you solve this problem, you'll get x bar, u bar, lambda bar. You got three equations, and you solve these three equations in three functions, three variables. Once you have those, you can actually find out. You can compute this. There's an example that I think that's given as an exercise somewhere, so I'm not going to get into that. And now we go back to our example, and we can see that as t goes to infinity, if rho is bigger than r, which means you are actually, your preference for consumption is higher than the interest rate. So the bank is not giving you too much. And you want to consume a lot more. Because consumption later, it doesn't really give you too much utility, because it can be discounted. So it's clear that in the limit, your wealth will go to 0, your consumption will go to 0. Remember, it will never be 0. It will only in the limit, it will be 0. But for any finite time t, this is still going to be positive. So when we say W bar, C bar, lambda bar, we're not using this control. Okay. We can use this control only if you begin with 0 wealth. But when you begin with 0 wealth, then we consume 0 wealth. And so it's a trivial problem. But if you begin with a positive wealth, like W0 bigger than 0, like here, then you will consume, but eventually As time goes to infinity, this thing will, in the limit, goes to 0. That's the case rho equal to r, where it's equal. That means that this is very interesting in some way if you think about it. If rho equal to r and you are given initial wealth, you're going to consume only the interest because r equal to rho. And the interest on W0 is RW0. So you'll only consume interest. You will never consume the wealth. The initial wealth W0 will stay all the way to infinity in the limit as well. You will when time in the limit as t goes to infinity, and if you are infinitely long-lived person, you will die with having this left. This wealth will still be in your portfolio. And there is no way to consume this wealth. See, what you can argue is this is kind of a paradox if you think about it. I'm consuming interest, right? But I have initial wealth. So I could theoretically consume interest and a little bit more from here, but a little bit more in such a way so that this W0 goes to 0 as t goes to infinity. That means I can try to consume my initial wealth so that I can consume a little bit more than rho W0, a little bit more than interest I get, in a way that W0 goes to 0. It turns out that any such solution is not as good as this solution. Because what happens is, if you consume a little bit more, then this W0 is declining. Not W0, WT over time is declining. So your consumption is, of course, it's rho WT plus a little bit of that, whatever the wealth was at that time. But nevertheless, altogether, it's going to be declining with this W0 is going to, this WT is going to 0. WT is going to 0 because you want to consume all of your initial wealth. And so there is no way, absolutely no way, that an infinite horizon person, when rho equal to r, can consume his initial wealth in an optimal solution. The guy will just stay with his initial wealth, whatever that is. And that is a stationary solution. If you look at some literature and search for something called a cake eating problem, you may find that this is kind of related to a cake eating problem. The cake eating problem is a cake that is going to be shared by infinitely many people. So you have a problem of a cake, then you share it by finite number of people, and then you let number of people go to infinity and find out, how you share that cake. Okay, so it turns out that everybody eats no cake, and the cake stays there forever. But anyway, now we have a slightly different problem. We now have a wealth which is invested in some market that gives you this kind of return. Don't ask me, it's just an example right now. And in this example, we can solve exactly these three equations. And these three equations gives us W star, C bar, lambda bar. You can see I'll now solve an infinite horizon problem. Okay? So if I begin with this W bar, 1 by rho, I have solved the problem completely. If I don't begin with this, then of course I have to go back to the solution. But in the limit, it will go this way. Any question? There's another concept that is important when it comes to infinite horizon. It's called golden path. The golden path says the following. It says that if I decide to choose an X, which is the initial wealth, okay, and I would like to keep that initial wealth so that initial wealth will stay exactly, my control will be such that I could keep the initial wealth. So the initial wealth will stay X all the time. And then you have a u sub X, which makes this 0, that u sub x you can put in there. And so then we have integrand phi xu in 3.8 becomes this. Now, that's only a function of x. The objective function now is only a function of x. And now I can take derivative with respect to x and maximize this business. Remember, the integrand is this. The integrand doesn't change. So maximizing the integral is same as maximizing the integrand. So what I'm trying to say is, golden path tells you the following. If somebody endows you with a certain wealth, and you are supposed to keep that wealth all the way to infinity, what wealth would you like to have? So the golden path is basically saying, give me that wealth to begin with, under the condition that I will only consume in such a way that my initial wealth stays exactly there. Then what wealth would I choose? God gives me wealth, and I can ask God, give me this wealth or give me that wealth, anywhere from 0 to infinity. And I will then choose a particular wealth, which gives me the maximum of this. Okay. So we already talked about this. We'll have more opportunity to figure out why the golden path and compare that with the optimal long-run stationary equilibrium, which is the one here, this given by this. We'll find out, what is going on here, what's going on there, and how these guys are related in some way. And that will come later in another chapter. This is a table we talked about last time. I want to point out only two parts of that table. And the one part is the following. First of all, there's a linear quadratic case, which is type C. This is a very standard problem in electrical engineering. It has a closed form solution. It also is very well known in inventory problems. It will call the HMMS rule, or Holt, Modigliani, Muth, Simon. They wrote a book, and they proposed something called a linear decision rule. So that problem has a special place in the literature in some way. It's completely solvable analytically, and so that's that. Now let me just do one more thing here. What if you have the absolute value function in your cost? So you have a control variable u, but the cost is absolute value of u. This happens when you buy and sell stock. If you buy a stock, this is let's say if you buy a stock, this is plus. If you sell a stock, this is minus. But the broker will charge a commission on the amount you buy or amount you sell. So if you sell and this is minus u, you cannot say commission is alpha times minus u, because that will be a commission that broker gives you instead of you giving to the broker. So you need the absolute value, alpha times the absolute value, where alpha is the commission on the magnitude of u. Well, this is not differentiable at 0. So what we do, there's some problem here. What's going on here? We have 3.2, 3.12. What? 3.12. Okay, Kushali,
Yes, Professor.
that comma is not supposed to be there, right? So please go back to the book and fix this remark, okay? And we'll talk about this later. I mean, it's okay. It's phi or f, and then the period, but then there's a new sentence that
Okay.
begins. So you remove the comma, and this W becomes capital W.
Okay. It's on slide 80, right?
It's on slide
80.
80. Book is fine. The book has no problem.
Okay.
Yeah. You see how little, sometimes these little things, you have an eye for this. Okay. So then what you do is you break this into two variables, U1 and U2. And then U becomes U1 minus U2, where both of them are bigger than or equal to 0. So this becomes buy, and this becomes sell, this becomes buy, this becomes sell. But of course, you don't want to buy and sell at the same time. So if I buy 5 units of share and sell 3 units of back immediately, then I'm paying the commission on 8. So that's not interesting, right? So what you want is, if you buy, then you don't want to sell. If you sell, then you don't want to buy. So you need this condition. But this condition is nonlinear. So if I want to break this down into two variables and I impose this condition, that makes the problem more difficult. But it turns out that you don't need to put this condition, because what happens is, when you break this down, the cost is given by U1 plus U2. So this is the cost. And if you want to minimize this cost, well, if you want to minimize the cost, this will automatically be satisfied. Suppose I want to buy 5 stock. Well, then this is 5 and this is 0. Okay, so the cost is going to be commission rate, whatever, let's say it's 1% times 5. Okay, now you will not be stupid enough to buy 8 and then sell 3. Okay, because then 8 plus 3 will be 11, and you're going to pay 1% of 11. Okay, that's not very interesting. So automatically, this condition automatically satisfied. We don't have to impose it, and so it's a standard practice to have absolute value function, break it down into like this, and then it works. So everything is differentiable then, and everything works. So this is one remark here. Another remark is, remember now, this is the linear Hamiltonian. And if I maximize the linear Hamiltonian, then it's a bang-bang control. But if this is vector and this is vector, what do you mean by bang-bang control? Well, it turns out the bang-bang control is actually a linear programming problem. So the bang-bang control generalizes to an extreme point solution. So when you solve a linear programming problem, you get a simplex, and you know that the solution is one of the corner points. So the corner point, in fact, is the generalization of a bang-bang in single variable case. There's one more remark, two more remarks. One is that if I have a salvage value which is given like this, well, that makes sense only in 2 cases. Because if t is fixed, you can remove that. Because it's only a function of what value x takes at that time t. T is not a variable anymore if t is fixed. But I keep this in the book. Even if t is fixed, I keep that because it saves me talking about this all the time, except I can put that in the remark one time and then I'm done with it. But if t is free and I want to determine t, then this is good, because that's the time, and t itself has to be optimized. Okay, and we have a condition in maximum principle that tells you what to do when I have to maximize also over t. When t is fixed, then you can remove that, and you can write it this way. Okay. Last remark is an impulse control problem that says that sometimes you can instantaneously use infinite amount of control. So let's say if you want to do advertising, you do infinite amount of advertising at a very small interval, which goes to 0. So it's kind of a limit, okay? You do an impulse control, which is infinite amount of advertising on a short time, such that as time sinks, the amount of control goes to infinity. But the product still is not 0 or infinity. It could be 0, but it costs money to do an impulse. So it's an infinite control, which may cost infinite amount, but it's exercised only a very short time. But that short time is going to 0. So the impulse control basically becomes an impulse. And we don't deal with the impulses in this, but there are problems in our literature. For example, SS policy. If you have an inventory problem in a continuous time and you have an SS policy, then if your inventory is below S, you order up to big S. That's an impulse control. So you need impulse control theory to solve that kind of problem. And there are papers by me and Ben Susan on inventory control problems using the impulse control, the methodology that this man, along with his advisor, developed in 1975. So these guys are known for their contribution to control theory. They are the ones who started the theory of impulse control, and they have a book on this topic. I think this book is probably a 1975 book. Okay. Any question before we go to chapter 4? Kusal, you're going to keep time for a break if somebody wants a break, okay?
Sure. Does anybody want a break before we switch to chapter 4?
Well, let's take a break a little bit later.
Okay.
It's usually halfway between. It's a good idea if somebody wants to go. And okay. Now, as I mentioned to you, that the pure state constraints are some of the most difficult problems in control theory. And no matter how I write chapter 4, I cannot do justice to the mathematics. But if I were to do justice to mathematics, the mathematics is so sophisticated that it will not be useful in a business school course. So chapter 4 is a huge compromise in terms of giving you theory with no proofs and intuition where possible, and then examples where we can use the theory to solve those problems. So that's the kind of a goal of this chapter. There is just, and there are a lot of references. You can, depending on how sophisticated mathematics that you are, you either go to those references, and in another case, if you need this particular theory in your research paper, you can find a math guy who's an expert in this area, and then you have a co-author paper, okay? So those are some of the ways you can handle issues of this kind. These days, it is, the number of co-authors on any paper is increasing over time. I don't know what is the average number of co-authors currently is, but the average number of co-authors have been increasing over time, partly because there are just too much literature all over the place that no one person or two person can be expert in many of these things. And so it's natural for people to collaborate, okay? So if different people can take different expertise, can combine and write a very nice paper or do very nice research. This is totally rewritten chapters, so if you previous book does not have any of these, I mean it's totally rewritten. So we begin with a problem first. We begin with a problem which is so simple that we can examine very quickly and find an optimal solution. And when we find an optimal solution to this problem, we try to see what the maximum principle should be. Because the maximum principle that we have developed so far is not sufficient to apply to this problem. And we will see why it is not so. Okay, so that's kind of the motivation of this chapter, is to begin with a problem to show you that I need to do something. I need to tweak my boxes of maximum principle in some way to handle the problems where I have constraint of this kind. This is called a state constraint. It does not involve u. It only involves x and time t. Okay. So let's look at this problem. The problem says that I want to maximize this function. Remember, there's minus u here. So I want to maximize this function means I want to minimize plus u. That means I want u to be as low as possible. So that's one thing that comes from here. Remember, as low as possible doesn't mean I can just change it everywhere. It only, in some sense, it's a dynamic problem. So there's a trade-off between what I can do now and what I can do later. But more or less, we would like, whenever possible and whenever feasible and whenever, whatever, we want it to be low. Okay. So now the other thing is that the constraint here. So the constraint is given by this parabola. And what we're now saying is that our solution for xt has to be about this parabola. Okay. For the time being, we're given x0 equal to 0. So let's look at that problem anyway. And when I have x0 equal to 0, what do I do? Well, first of all, you can sort of see that x dot is u. So if I put u equal to 0, x stays at 0. So there's no problem for me to keep u equal to 0 and stay there. Remember, u cannot be below 0. Otherwise, I would like to do that. But it is between 0 and 3. So the best I can do is to use 0 until here. Once I come here, well, if I keep using 0, then I will come here. If I come here, then I cannot be above this curve. So the best thing for me to do is to ride along this curve. But I don't want to lift and go further because that would need more control. So the best I can do is to use a control so that doesn't lift myself from this, but I can ride along this curve. Well, that's very easy because I can ride along this curve by taking the derivative of this. When I take the derivative of this, I get this. Because x dot is u. I take the derivative of this, x dot is u, and then take the derivative, this is 2 times t minus 2. And that must be non-negative. Okay. And that gives me, so you make this bigger equal to 0, but I want to ride along the curve so that I want to make it equal to 0. Then ut is exactly 2 times 2 minus t. Notice now, this is t minus 2 because if I go bring it to that side, this will be minus of 2 of t minus 2. That becomes 2 of 2 minus t. Okay. It is sometimes not easy to see that. Sometimes people say, oh, there's a mistake here. But until you carefully see that, actually, it would be better if I put minus here and then put t minus 2 and then make it one more line to make it easier to follow, but that's okay. So I can ride along this. But notice if I ride along this up to here, and then if I ride along there, then control has to become negative because I have to go down and I'm not allowed. Or I can have a positive control and go up like this, but that is going to cost me money. So I just use u equal to 0 all the way up to here. So you can see that in this problem, The optimal control is given by this trajectory. This is the state, optimal state trajectory, and the control is given by this. So this is the trajectory, this is the control. Now I want to find the value function. Now the value function usually you find for every x and t in this space, feasible space. That means I could have x and t here, I could have x and t here, I can have x and t here. I mean up to 0.3. I can have xt here, wherever, okay? And from that point, I need to find out an optimal solution and take the value of the optimal solution. Take the value of the optimal solution, and then I go from here to, for example, if I'm here, I'll just stay 0 all the way up to here. That's my control, and I can compute the value, and that gives me the v of x of t at that particular point. If I'm here, I already know that. If I'm here, xt here, so xt means x is here and t is here, then you can easily see that I will use 0 up to here, and then I use this control, and then I use this control, and I can find the value of that control. If I'm here, anywhere here, in this triangle, I simply go all the way up to here with the 0 control. So if I'm here, I just go here like that, and I can compute the value of that. Now, in order for me to make my life simple, and that particular thing is right here, you can see what I did here. We can limit its range to x bigger than 0 in view of x0 equal to 0 and u bigger than equal to 0. I don't want to give you the value function here. You can do it, but I don't want to spend 2-3 pages to do that. Okay, so I'm basically limit myself to this space. And if I begin with 0 and above, I will not go below. So I can find the vxt for x bigger than equal to 0 and a t bigger than equal to 0. Okay, so I can limit myself to this. Vishali, you're going to put that line in the slide, okay?
Okay, Professor.
Yeah, make a note of that.
Right, that's from the email that you sent today.
Yeah.
Okay.
Okay, so we have all of that, and so we can basically compute a vxt. So you can see I compute vxt. I start from a t to tau, and the tau is the time at which, so if I begin with a t, then tau will be the time at which I hit this point. So I have to take that integral with a 0 control. Then I have to take the integral from here, from tau to this place, and then 0 again. So if I take the vxt, I get this. So the value function is given by any xt in the feasible space, including this triangle. I can have xt in this triangle, and here, or here, and here, anywhere here. I can go anywhere up. So for all of those values, I have a vxt. You notice there is a thing here, and that's the reason. The reason you have that is because, so once we do this, then let's see what happens when x is between 0 and 1, and it's on the left side of the parabola. Then optimal trajectory is very similar to one I already had this. If it's the left side of the parabola, and it's easy to find the vxt for that. The control is 0 until it hits the boundary, and then the control switches to this from this to climb along the left side of the parabola to reach its peak, and then back to 0 on the time interval. Yeah. Okay. So when t is between 0 and 2, when t is between 0 and 2, you can sort of see that I don't allow the x here. I only allow the x here. So that's the reason why I'm giving you here this condition here. This basically said that anywhere here, xt can be defined by this condition. Okay, so all of this is done. Then once I have the value function, I can take the derivative. Remember, the derivative is supposed to be lambda, the shadow price, the adjoint variable. And the lambda in all the way from chapter 1 to 3 is continuous because lambda dot is a differential equation and a solution of a differential equation is continuous. But now see, if I take the derivative of this with respect to x, that should give me the lambda. But if this lambda is actually discontinuous at point 2. You see, Vx is 1 up to this 2, and then at 2 it goes to 0. So at t equal to 2, the marginal valuation is discontinuous. And that's just the nature of the beast. You know, depending on where you are, you compute the marginal valuation, and that gives you the value of the state, increment on the state at that point in time. At that level of x, I mean by that. Okay. So we need to allow the lambda to be discontinuous in the maximum principle that we developed. Now, if you were to prove the maximum principle from first principle, you will even get there. But the proof is going to be massively complicated. And as I can tell you, the state constraint theory continues to develop because it's not fixed. Fixed in the not, I didn't mean fixed. I mean it is still evolving. People find new results, little thing here, little thing there, and then they keep writing papers, and you know, it's like keeping up with the current literature. But once again, it's highly mathematically it demands, it's challenging. So we're going to take the root approach that we are taking. So now, having this idea in mind, we're going to develop the maximum principle. And for that, we're going to start with a general problem of state constraint. And the general problem of state constraint is this kind of state constraint. See, here is this constraint. No, I'm sorry. I have to go back to here now. So this is the constraint, which is now going to become h of x sub t. This is the constraint. Okay, couple of things. One is that if I want to maintain this constraint when I'm at the boundary, I have to control its derivative. Now, if I take the derivative of that and I don't get any u in that, when I substitute for derivative of this, whatever that derivative is, and the derivative will be this, for example, dh dt is given by this. And when I substitute, now this f has a xut, but maybe it doesn't, maybe things can cancel out from here and here. And so this may not depend on u. If it doesn't depend on u, then I cannot control the derivative of this by changing u. So then what I do is I take the next derivative, h2, take one more, and find out if there's a u appear in this right-hand side. So what I do is then I control the h2 dot, which is the acceleration of this h. Then that gives me the change in velocity, and then the finally change in h. So you see, depending on the function h and the function f, this constraint could be more complicated than we are going to deal with. So we're going to assume that our constraint is order 1. order one means H1 will automatically have a U in there. If you take as many derivatives as needed before you get U here, and if the number of derivatives needed is R, then R is the order of the constraint. Okay, and there's the theorems, and there are available literature has all of these available. If R is more than one, you have to go and develop those things, but we will limit. I have not, there are problems that I've looked at. There are some applications that I know about, but in this book, we're going to assume R equal to 1. And there are references I give you, so you can go there if your problem that you formulate for your research doesn't have that feature. The most special case of this constraint is xt being bigger than or equal to 0. This is the special case of this constraint. Another special case of this constraint is xt less than m. So this lower bound, this upper bound. And if it's this kind of thing, then h1, which is the first derivative, is minus f. Because this derivative of this is 0. Okay, so those are some of the things. And one more thing that we want to talk about is, I don't have a picture here, but maybe the picture is not there anymore. Some terminology. If the ith constraints, because h is, remember, h can be multidimensional. It's more than one constraint. So this means there are p constraints. Okay, that means there are p constraints. Okay, xn means n variable here, t means 1, and there are p such constraints: h1, h2, h3, hp. Okay, but I1, 2, 3, p. Okay. So then we have, if a particular ith constraint is bigger than or equal to 0 on this interval, then this is the interior interval, because it's an interior of the constraint. If the optimal trajectory hits the boundary, which means at some point it becomes 0 at between tau 1 and tau 2, then the tau 1, tau 2 is called a boundary interval. So if you look at our example here, this is the interior, because, and this is the boundary interval. See, 1 to 2 is a boundary interval. Then this is back into the interior. Interior is all here, because this is not infeasible. This is boundary, and the interior of the boundary is here, which is inside the boundary. Okay. Don't look at it this way, because it's a greater than or equal to 0. So the interior is on this side. If it's less than or equal to 0, the interior will be on this side. This is not, it's only a terminology, and it is good to know what it is. If this is the case, then tau 1 is called the entry point. And a boundary was starting at tau 1, tau 2 is called exit point if the boundary interval ends and an interior interval starts at tau 2. So when you exit, so this is exiting the boundary. I'm exiting the boundary here, and I'm entering the boundary here. So that's tau 1, that's tau 2, that's the entry point, that's the exit point. What else? Junction point. If I had a control that went like this, and then went like this, so it stayed on the boundary only at one point in time. There could be another objective function that will do it for you, right? If that's the case, then that's called a contact point. So that's a contact point. And if you put all of these together, we call them junction types. So junction can be entry point, exit point, and a contact type. That's a general term for these three guys. For existence problem stuff, again, we have a full rank condition. The full rank condition should be of the tight constraints. So if I have a, if I have a up to p hat, if there are p hat constraints, which are, I reorder the constraints so that the first p hat constraints are tight, which means they are equal to 0, and these are interior, not tight, then the tight constraints, their derivative with respect to U, that matrix should have a rank of P hat. Okay, so we're not using so much of these kind of things, but you need to have that if you want to do research, and you kind of check if that is true. So now we have a problem. This is a problem that we want to deal with. I think this is a good time to take a 5-minute break. Is that okay? Okay? Hello?
Yes, Professor.
Let's take a 5-minute break, or if they want 10 minutes or 5 minutes. What is that? What is our system? I'm okay with either one.
Depending on how tired people are.
Okay. Okay. Let's do 10 minutes, okay?
Okay, it's 2:06. We'll be back at 2:16.